All right. Hello, physics students. This is video lesson 7.05. What we're going to find is the work energy theorem. We're going to discuss what this is. Let's talk about what we know about work already. We know that if we take the force that's parallel to the motion, and we multiply that by the distance, and I'm going to change this to x now. A lot of times in some textbooks, you'll see it as d, and in some textbooks, you'll see it as x. Remember, we also said that you see it as f cosine theta x. And this is if you've set up your angles so that the portion that's causing the motion is a cosine function. So I prefer to write it as the parallel force times x is equal to work. We also said back at the beginning that work is the ability to do work is an expression of energy. And in order to see energy, we either have to have a reference point or we have to be able to see some kind of a displacement, and we see that here. Well, if work is an expression of energy, this also has to be equal to energy in some capacity. And because we're talking about work as the aspect of energy causing motion, the other thing we can talk about is it's equal to delta KE. So delta, in case you haven't picked this up yet, is always equal to the change in. So change in. So this means that if I take my final kinetic energy minus my initial kinetic energy, now initial or original, you'll see this as KEI or KEO, initial kinetic energy or original kinetic energy. But you always see the final as KEF. But keep in mind, I can rewrite this because there's a formula for kinetic energy. So I could bring this down into, I could say this is also equal to, keep it on the same line, 1/2 mv final squared minus 1/2 mv initial. And I'm going to use the O here to show you that it can be either I or O. So this is a pretty, it's a big equation. This is why memorizing equations doesn't work. You have to understand that work and kinetic energy, change in kinetic energy are the same thing. And then you have to be able to bring these equations together. So if I do an end-to-end combination, what I'm going to have here is that the force that's parallel times the displacement is equal to work is equal to delta KE is equal to 1/2 mv final squared minus 1/2 mv initial squared. And this really is consistent with what we talked about back at the beginning, where to see energy, we have to be able to have a reference point in the case of like potential energy or spring energy, or we have to be able to see it doing something. And that's what we have here. So we're seeing the movement. So here we're looking at the velocity, here we're looking at the displacement. Remember, velocity is displacement divided by time, and that's further going to connect these two equations. So what I want to do then is I just want to work some sample problems that are going to help illustrate this equation. So let's start off with a mathematical one. A 5-kilogram object is sliding across a floor at 10 meters per second. How much work is done by friction to bring it to a stop? So let's go with our equation again. Force parallel x equals work equals delta KE equals 1/2 mv final squared minus 1/2 mv initial squared. So really the question is, what portion of this equation are we going to want to use? Well, I have a mass of 5 kilograms. I have bringing it to a stop. So my final velocity is 0 meters per second. My initial velocity is 10 meters per second. I'm checking all of these boxes. So I have all of that. So they want to know the work that's done by friction. So that means I'm using this part of the equation. So when I plug in my variables, I'm going to have, I can just simplify it to be work is 1/2 mv final squared minus 1/2 mv initial squared. And when I plug in my values, I get 1/2 5 0 minus 1/2 5 10 squared. And when I solve, I get, now since we're doing work, remember work is usually in Newton meters. and energy is usually expressed in joules. And they mean exactly the same thing. We just tend to associate Newton meters with work and joules with energy, but I get negative 250 Newton meters. And this is consistent because if I put a motion vector here, so if this is my box, and I'm moving this way, we know that friction is operating this way. So the force of friction is going to be this way. And because friction is in the opposite direction of motion, a negative work would be correct. So we know that we've set this up correctly. All right, the next sample problem, well, I gotta figure out what I did with my sheet. There it is. Has this graph. And this requires us to talk about another aspect of work and kinetic energy. So it says a graph of the net force exerted on an object as a function of x position is shown for the object of mass m as it travels a horizontal distance 3d, which expression represents the change in kinetic energy of the object. Well, this is going to be tough for you to answer until you know that the area under a F force versus displacement graph equals work. So if we find this area, that all of this is going to equal my work, and work equals the change in kinetic energy. So which expression represents the change in the kinetic energy of an object? So I need to find this area. Well, they're giving you the answer in terms of FD. So if I block this off, here I have, they want to know how many, we have coefficients. So we have 3FD, we have 3.5, we have 4.5. So one block, if I multiply this, a different black marker about done. That's going to be 1 FD. That's going to be 2. That's going to be 3. Here's 4, and that's a half. So the correct answer is going to be 4.5 force times distance. And how do we know that? Because this area is equal to work, and work is equal to the change in kinetic energy. All right, let's do one more sample problem. These are a little hard to read. I do apologize for that. I'm going to hit the focus button and see if I can clean this up a little bit. Not much. A block of mass m is sliding along with an initial speed v sub f along a horizontal surface with negligible friction. So let's get a motion vector here. Here's my block. So we don't have friction. A constant force of magnitude FA is exerted on the object at an upward angle of 60 degrees from the horizontal, causing the object to speed up. If the block remains in contact with the floor, what is the change in the block's kinetic energy as it moves a horizontal distance delta x? All right, so my force parallel times x equals work equals delta KE equals 1/2 mv final minus 1/2 mv initial. So, okay, you get the idea. And what we know is that we have, so what are our knowns? We have FA, it has theta of 60 degrees. We have the initial, V initial is equal to VI, it's just VI. And we want to know what is the change in the block's kinetic energy as it moves. So we want to know delta KE as it relates to X. Well, it talks about velocity, but if we look here, we're talking about a force and we're talking about displacement. And so it makes more sense to use this half of the equation. And we're talking about kinetic energy, but remember, we can say kinetic energy is also equal to F parallel X. if we look at our answers, let's start here at D. So we've got 1/2 mv initial squared. So we've got the initial kinetic energy plus FAX. Well, right away, we should be able to toss this out for this reason. Is the entire applied force at work here? So if I was doing a free body diagram, go back to red, I've got my normal force, I've got my weight vector, and then I've got this applied force. That's not 60 degrees. So this is going to be FAX and FAY. So right away, if we look at this, this FAX, no, it's going to be a portion of it. So we can eliminate that. And so by default, this has FAX, we can eliminate that. So that leaves us with 1/2 FAX or 1/2 mv final squared plus 1/2 FAX. So what this is saying is we're going to use a portion of that applied force, and that makes sense. So usually on these problems, you can toss out two answers pretty easily, and the other two you have to kind of think about. So they're saying that I need to take this and this to solve for this. Well, if you look at this equation, that just doesn't make sense. I could say that the kinetic energy is simply equal to the change, or is simply equal to the force times the distance. So really, all I need is this. So the answer here is going to be A. All right, let's do some more practice with the homework problems. And in the next video, we'll start working now with conservation of energy. Thanks for watching.